Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Mercury is a planet of extremes, a world baked and battered by a sun that dominates its sky, sculpted by a history of violent impacts, and yet marked by subtle complexities that continue to surprise scientists. It is the smallest of the 8 major planets in our solar system, a rocky orb that clings tightly to the sun in a swift, elliptical orbit. From a distance, it appears as a pale, cratered disk, a little like our moon, but up close, Mercury reveals a story that is both raw and refined, a record of the early solar system preserved on its surface, an internal structure that challenges simple expectations, and an environment that blends extremes of heat and cold, day and night, emptiness and thin, whispering atmospheres. Calling Mercury the Scorched planet captures an essential truth about its existence, but it also risks flattening a much richer, more surprising identity. To know Mercury is to travel through time and to probe the full range of planetary possibilities, from formation through tumultuous youth to the quiet endurance of its ancient crust. Mercury's proximity to the sun defines much of what it is. With a semi-major axis of about 0.39 astronomical units, that's 39% of the Earth-Sun distance, it orbits with a rapidity that astonished early observers and still delights astrophysicists. A year on Mercury, the time it takes to complete one orbit around the sun, is just 88 Earth days. Yet a single day, measured from one sunrise to the next at a given longitude, is far longer because of the planet's slow rotation. Mercury is locked into a 3-times spin-orbit resonance, rotating 3 times on its axis for every 2 orbits around the sun, a gravitationally induced dance that results in peculiar patterns of solar heating across its surface. This orbital intimacy produces extremes, a blazing daytime hemisphere where temperatures rise above 400 degrees Celsius, and a night side that plunges hundreds of degrees below freezing. Despite these extremes, Mercury is not simply a dead, featureless rock. It records geological processes, hosts a magnetic field, and maintains a tenuous exosphere formed from particles knocked off its surface. Each of these features opens a window into planetary physics under conditions very different from Earth's. The surface of Mercury reads like a history book written in impacts. For much of its visible face, the story is one of relentless bombardment. Craters of every size pepper the landscape, from tiny pits to colossal basins that span hundreds of kilometers. Some of these basins are multi-ringed and ancient, their floors smoothed by later deposits or shattered by subsequent impacts. The best known of these is the Caloris Basin, a vast circular depression more than 1,000 kilometers across, created by a cataclysmic collision early in the planet's history. The energy that formed Caloris would have vaporized rock and triggered seismic waves that circled the globe. Its antipodal region, the part of the planet opposite the impact site, bears strange hilly terrain that may be a direct consequence of those shock waves refocusing there. These features testify to an early epoch when the inner solar system was a more violent place, when planetesimals and protoplanets collided with such frequency and ferocity that they reshaped planetary surfaces and sometimes entire internal structures. But Mercury's surface remembers more than impacts. It preserves evidence of volcanic activity and crustal modification. Smooth plains, some of which border or fill basins, point to episodes when molten rock flowed across the landscape, quietly burying older reliefs. These volcanic plains are generally less extensive than those on the moon, yet they indicate that Mercury once had internal heat sufficient to melt rock and create surface flows. Long, cliff-like features, known as lobate scarps, crisscross the planet. These scarps are thrust faults formed when the planet's crust contracted, pushing one block of crust over another. Their presence reveals that Mercury cooled and shrank over time. The planet's interior lost heat and contracted, causing its brittle outer shell to crumple. The length and distribution of these scarps suggest a global contraction amounting to a few kilometers of radius change. Small in planetary terms, but significant for a body of Mercury's size. Together, the craters, plains, and scarps outline a narrative of a planet that formed hot, gradually cooled, and retained the footprints of both violent and subtle internal processes. The interior of Mercury is where it becomes truly puzzling. Relative to its small size, Mercury's core is unusually large. Rough comparisons of mass and radius indicate that the metallic core occupies a much greater fraction of Mercury's volume than Earth's core does of our planet. Early models suggested a large iron core surrounded by a thinner silicate mantle and crust, but measurements from spacecraft have revealed additional complexity. The existence of a global, albeit weak, magnetic field strongly implies at least part of the core is molten and electrically conductive, sustaining a dynamo, an active process where convective motion within a conducting layer generates magnetic fields. The presence of such a dynamo on a small world like Mercury was unexpected because small bodies are thought to cool quickly and solidify internally, shutting down the convective motions required for dynamo action. To explain Mercury's magnetic field, scientists have proposed several ideas, perhaps radiogenic heating, tidal interactions with the sun in early epochs, or chemical composition differences, including sulfur or other light elements in the core lowering its freezing point, allowed a molten outer core to persist. Some models suggest a solid inner core surrounded by a molten outer layer, an arrangement that could sustain a dynamo under the right thermal and compositional conditions. Details remain an active field of research, and each new measurement refines our understanding of how small planets remain magnetically active. Mercury's magnetic field is weaker than Earth's, but surprisingly structured. Rather than a simple dipole centered at the planet's center, Mercury's field appears to be offset somewhat toward the northern hemisphere. This asymmetry affects how charged particles from the solar wind interact with this planet and shapes the landscape of the exosphere and surface sputtering. The magnetic field also creates magnetospheric phenomena, regions where trapped charged particles and electromagnetic interactions sculpt space around the planet. Though Mercury's magnetosphere is far smaller and more directly influenced by the solar wind than Earth's, sudden variations in solar activity can compress or distort the magnetosphere dramatically, leading to energetic particle bombardment of the surface that can liberate atoms and molecules from the regolith. These processes feed into Mercury's exosphere and help texture the planet's surface chemistry. Unlike Earth, Mercury lacks a thick, persistent atmosphere. What it has instead is an exosphere, a tenuous shroud of atoms that rarely collide with one another, more like a cloud of individual particles than a continuous gas. This exosphere is composed of atoms sourced from the surface and from solar wind interactions. Sodium and potassium have been detected in Mercury's exosphere, along with calcium, magnesium, and even trace amounts of water-related species. These atoms are liberated by micrometeoroid impacts that vaporize surface material, by photons from the sun, knocking atoms loose in a process called photon-stimulated desorption, and by the sputtering effect of energetic particles from the solar wind. The exosphere is dynamic, responding to daily cycles of sunlight, to the planet's position along its eccentric orbit, and to variations in solar activity. In localized regions, particularly near the poles and permanently shadowed craters, ice and other volatiles can persist because temperatures there remain low enough to prevent sublimation. The discovery of water ice and darker organic-rich materials in some permanently shadowed polar regions was a surprise to many and provides a striking counterpoint to the scorched image of the planet. Mercury's thermal environment is complex. On the sun-facing side, temperatures can soar well above 400 degrees Celsius, hot enough to melt lead. Yet at high latitudes and inside permanently shadowed polar craters, temperatures can fall below 170 degrees Celsius, cold enough to preserve water ice indefinitely. This coexistence of extremes arises because Mercury's axis is almost perfectly upright with respect to its orbital plane. It has almost no axial tilt, so sunlight sweeps across latitudes in a straightforward way. The slow rotation also means that any given spot experiences prolonged daylight and prolonged darkness during a single Mercurian day, exaggerating diurnal temperature swings. The result is a planet where the most sun-warped plains bake and the shadowed polar niches shelter ice. Thermal gradients like these affect surface chemistry, physical weathering processes, and the mobility of volatile compounds. Mercury's surface composition is another source of fascination. Spectral measurements and spacecraft data indicate that Mercury's crust is chemically distinctive. It contains higher than expected sulfur and low iron content in silicates compared to many other terrestrial bodies, and its surface reflects a low albedo in some regions. These compositional clues hint at how Mercury formed and evolved. One hypothesis holds that Mercury initially had a composition similar to other terrestrial planets, but lost much of its silicate mantle through giant impacts or intense solar heating during the chaotic early solar system, leaving an iron-enriched remnant. Other theories suggest that Mercury formed in a metal-rich region of the protoplanetary disk, where metal condensed more readily than silicates, or that processes like evaporation selectively removed lighter elements from its surface. The exact path remains debated, but measurements from orbiting spacecraft like Messenger have enriched the data set, revealing elevated sulfur and potassium, and a surface chemistry that challenges simple evaporation scenarios. These chemical fingerprints, are keys to unlocking Mercury's origin story. Human knowledge of Mercury has come in dramatic leaps, thanks to spacecraft missions that closed the distance and brought instruments to bear. The first spacecraft to visit Mercury was Mariner 10 in the mid-1970s. Mariner 10 used a gravity assist from Venus to reach Mercury and performed multiple flybys, mapping about 45% of the planet's surface and discovering the magnetic field. Its images revealed a heavily cratered surface in the dramatic Caloris Basin, but much of the planet remained unseen. Decades later, the Messenger mission, which entered orbit around Mercury in 2011 after its own series of gravity assists, transformed our understanding. Messenger mapped the entire planet at high resolution, measured surface composition, analyzed the magnetic field in the exosphere, and provided critical insights into Mercury's geologic history and internal structure. It found evidence for volatile elements, mapped the distribution of water ice in polar regions, and documented the scarps and volcanic plains that tell the tale of a cooling, contracting planet. Messenger's data have been a treasure trove, reshaping models of planet formation and evolution. Following Messenger, additional missions have carried human curiosity closer still. International collaborations and advanced spacecraft designs promise to refine our knowledge of Mercury even further. These missions aim to probe Mercury's internal structure with greater precision, to map its surface in different wavelengths, and to better understand how the solar wind and magnetospheric interactions sculpt its exosphere. The continuing study of Mercury is not merely an exercise in planetary archaeology. It is a necessary element in building a full theory of how rocky planets form and evolve in the presence of a dominant star. Every planet in our solar system provides a data point, and Mercury, with its unusual characteristics, is especially revealing. One particularly intriguing aspect of Mercury is its surface features known as hollows. These are shallow, irregular depressions often found clustered on crater floors and on the rims or walls of impact basins. They are seasonal in appearance in the sense that they are relatively young features. They appear to be little eroded, sharp-edged, and bright in reflectance compared to the older parts of Mercury's surface. Hollows are associated with low reflectance material and sometimes appear alongside features indicative of volatile loss. Scientists interpret them as regions where volatile materials sublimated or were otherwise lost from near-surface deposits, perhaps through interactions with sunlight, the solar wind, or thermal processes. Because hollows require volatile-bearing materials near the surface to form, their existence has been a clue that Mercury, contrary to older assumptions, retains significant volatile species in some locales. This realization complicates the narrative that Mercury's closeness to the Sun would have stripped it clean of such materials during formation. Mercury's relationship to the Sun also gives it a peculiar role as a laboratory for extreme space weather. Being so close to our star, Mercury experiences intense fluxes of solar radiation and a high density of the solar wind, the stream of charged particles flowing outward from the Sun. The magnetosphere, thin exosphere, and the bare surface itself interact with these inputs. During times of heightened solar activity, energetic particles can strike the surface with greater vigor, sputtering atoms and altering surface chemistry. Solar storms can compress the magnetosphere to the point where the solar wind impacts the surface directly at certain latitudes, leading to localized enhancements in exospheric species. These processes are of scientific interest, not only for understanding Mercury, but also for appreciating how stellar environments can shape the evolution of planets more generally, including exoplanets orbiting close to their parent stars. Thinking about Mercury also invites reflection on comparative planetology, how studying one planet can teach us about others. Mercury, Venus, Earth, and Mars are siblings in a sense, formed from the same protoplanetary disk, but diverging through difference in size, composition, initial conditions, and subsequent evolution. Mercury's large core fraction invites comparisons with the massive cores of iron-nickel exoplanets discovered in recent years. Understanding how Mercury formed may shed light on the diversity of rocky worlds across the galaxy. Mercury's tenuous exosphere offers an analog to the transient atmospheres we might find around small, airless bodies elsewhere. The planet's thermal extremes are a cautionary lesson for considering habitability zones and the survivability of volatiles. In short, Mercury amplifies fundamental questions about planetary differentiation, volatile retention, magnetic dynamos, and surface-atmosphere interactions. Culturally and historically, Mercury has always been a source of fascination. Ancient observers saw it as a swift point of light that traced strange paths across the morning and evening skies. In various mythologies, it took on identities associated with messengers and tricksters, a reflection of its rapid motion and elusive appearance to the naked eye. Modern spacecraft visits have demystified the planet in some ways, but in others have revealed new mysteries that deepen our curiosity. Mercury is less accessible than the outer planets in terms of delta V and thermal constraints. Yet precisely because of these challenges, missions to Mercury require innovation in engineering, trajectory design, and thermal protection, advancing technology even as they expand knowledge. The conserved scars on Mercury's face invite us to imagine the conditions of the early solar system, when collisions were common and planetary embryos jostled for dominance. The presence of both ancient cratered terrains and younger volcanic plains tells of a world that was geologically active enough to refresh parts of its surface, but not sufficiently vigorous to erase all traces of its past. Its magnetic field suggests an interior that retained dynamism under unexpected conditions. The discovery of water ice in shadowed craters alongside sun-baked plains underscores the complexity that can exist even on a planet that seems defined by one overriding trait: scorching proximity to the sun. Looking forward, Mercury will remain a focus for planetary scientists. Each new observation refines models, and each puzzling measurement propels new hypotheses about composition, thermal evolution, and core dynamics. More advanced instrumentation could probe seismic activity, if ever a lander or network of landers were feasible, to provide direct constraints on internal layering and core size. Improved spectrometers could further distinguish surface mineralogy and the distribution of volatiles. Continued study of the exosphere will enrich our understanding of surface-exosphere coupling and space-weather interactions. Even without human boots on its ground, Mercury offers a natural laboratory for processes that could be universal, especially around stars more luminous than the sun, or in planetary systems tightly packed near their host stars. Ultimately, Mercury challenges simple narratives. It is indeed scorched in places. Its daylight temperatures and constant exposure to solar radiation make the adjective apt. Yet the planet is also cool in other regards, literally in permanently shadowed regions, and cool in the sense that it preserves ancient history and subtle signs of internal life. Its large core and unexpected surface chemistry press against tidy formation models and force refinement of theories about how terrestrial worlds come to be. Its magnetic field and exosphere complicate our understanding of small planet magnetic dynamos and atmospheric retention. Mercury is a study in contrast, hot and cold, dead and dynamic, simple in size yet complex in nature. To see Mercury is to see the raw interplay of star and planet, a vivid demonstration of how proximity to a star can both strip and sculpt, heat and preserve, reveal and conceal. For scientists, it is a reminder that planetary systems harbor diversity beyond initial expectations, and that each oddity observed in our nearby solar system likely foreshadows even stranger configurations awaiting discovery among the stars. For anyone who gazes at the morning or evening sky and spies that fleeting twilight dot, Mercury offers the promise of stories written in fire and silence. A scorched planet whose quiet mysteries continue to speak across space and time. Under the relentless radiance of the sun, Mercury continues to present mysteries that bridge ancient processes with ongoing interactions. Extending our exploration of this scorched world requires delving deeper into its thermal environment, orbital dynamics, internal structure, and the implications these factors hold for planetary science at large. While the core features of Mercury have long been known, recent studies and mission data have pushed scientists to reconsider earlier assumptions and embrace more nuanced interpretations of how this hot, compact world came to be and how it behaves today. The subtleties of Mercury's behavior offer an expansive narrative, one that enriches our understanding of rocky planets by revealing how variation in size, composition, and solar exposure creates an entirely different evolutionary pathway. One particularly striking aspect of Mercury's identity is its resonance-driven rotation. Most people are familiar with the concept that the moon keeps the same face toward Earth, locked in synchronous rotation. Mercury's 3-2 spin-orbit resonance, however, is subtler and far more complex. Early astronomers believed Mercury was tidally locked to the sun in the same way the moon is to Earth, showing only one hemisphere to the star. It wasn't until radar observations in the mid-20th century that scientists realized the planet rotates 3 times for every 2 orbits it completes. This peculiar rotational state arises from a combination of Mercury's orbital eccentricity and the gravitational influence of the sun. The result is that certain longitudes experience especially long days, with the sun lingering near the zenith for extended periods, while other areas undergo protracted stretches of dawn or dusk. This interplay of rotation and orbit shapes not only the thermal regime but also contributes to weathering, chemical gradients, and space weather interactions. Another compelling dimension of Mercury's story lies in its crustal structure and tectonics. While Earth has plate tectonics and Mars once had extensive volcanic and tectonic activity, Mercury's geologic evolution took a different route. Its lobate scarps, those great cliffs that curl across the surface, are visible evidence that the planet has been contracting for billions of years. Scientists estimate that Mercury shrank by several kilometers in radius as its interior cooled. The lobate scarps appear crisp and relatively undegraded in many locations, suggesting that some of this contraction occurred more recently in geological terms. Crustal shortening on a global scale hints at a planet that remained thermally active far longer than expected for such a small body. This also suggests that the interior structure allowed heat retention far into Mercury's middle age, driving both contraction and volcanic resurfacing. These tectonic features intersect with Mercury's volcanism, producing a complex tapestry of resurfacing events. Lava plains, both smooth and rough, blanket vast areas. Volcanic vents, some explosively formed, punctuate the landscape. Their presence indicates that Mercury experienced both effusive and explosive volcanic activity, meaning molten rock did not simply ooze across the surface, but sometimes erupted with significant force. This explosive volcanism is surprising because it implies the presence of volatiles deep within Mercury, a contradiction to early theories that the planet should be almost entirely dry. The detection of pyroclastic deposits, which are materials ejected during explosive volcanic events, underscores that Mercury harbored trapped gases, likely sulfur or other compounds, within its magma. These insights reshape our understanding of how heat and chemistry circulated through Mercury's interior. Mercury's exosphere, thin though it is, plays a role in shaping surface features as well. Sodium and potassium, when illuminated by the sun, can form a glowing tail that stretches away from the planet, similar in appearance to a comet's tail, but for very different reasons. This tail provides real-time insight into how solar radiation pressure acts on surface-derived particles. Observations reveal that the intensity and shape of Mercury's sodium tail vary with the planet's position in orbit, reflecting changing solar wind pressures and the angle of sunlight. These dynamic changes illustrate that even on a seemingly inert airless world, atmospheric-like processes can occur when solar forces dominate material behavior. The study of Mercury's magnetosphere deepens this dynamic picture. Unlike Earth's robust magnetic shield, Mercury's magnetosphere is a compact, tightly pressed bubble shaped constantly by solar wind pressure. During intense solar events, the magnetosphere can be compressed to the point where solar wind particles directly reach the surface at certain points, an event that would be catastrophic for Earth's biosphere, but is simply part of the normal environmental cycle on Mercury. These interactions generate bursts of energetic particles and contribute to surface sputtering, altering both chemistry and the exospheric composition. They also create magnetic reconnection events in which magnetic field lines break and reconnect, releasing energy and reshaping the magnetosphere. Mercury thus becomes a natural laboratory for studying the borderlines between planetary magnetic fields and stellar winds, a relationship that has profound implications for exoplanet research. The temperature regime on Mercury also invites deeper consideration. The extreme heat of the day side and the piercing cold of the night side create stress fractures, break apart rocks, and contribute to a cycling of surface materials unlike anything seen on Earth. Thermal fatigue, a process where rocks expand and contract repeatedly, causes them to crack and crumble into finer grains. These grains contribute to Mercury's regolith, the thin layer of dust and broken rock that covers much of the surface. The regolith, in turn, becomes the material sputtered into the exosphere by solar wind and micrometeoroid impacts. Over time, these interactions create a feedback loop, where thermal cycling creates new surface materials, impacts distribute and pulverize them, and the solar environment lofts atom-sized particles into temporary orbital paths before gravity draws them back down. Even with our growing knowledge, questions linger about Mercury's formation. One influential hypothesis argues that Mercury endured a giant impact early in its history, an event energetic enough to strip away much of its outer mantle and leave behind an iron-rich core supporting a relatively thin crust. Numerical simulations support the plausibility of such an event, suggesting that debris from the impact could have spiraled into the sun or been blown away by early solar winds. An alternative theory holds that Mercury formed in a region of the early solar nebula where temperatures were so high that only metals and certain minerals could condense, resulting in a naturally iron-enriched planet. Yet another perspective suggests that photoevaporation from the young sun stripped lighter elements from Mercury over time. Each of these models has merits and challenges, and current data point to a combination of processes rather than a single decisive event. Understanding Mercury has ripple effects across planetary science, especially in the context of exoplanets. The discovery of super-Mercuries and ultra-short period planets orbiting close to their stars hints that Mercury-like bodies may be common throughout the galaxy. These planets often have high densities, suggesting iron-rich compositions. By studying Mercury, our local analog, scientists gain a reference for interpreting the telescopic signals of distant worlds. Mercury's interplay of heat, magnetic fields, volatiles, and internal structure becomes a comparative framework that helps researchers understand how rocky planets respond to intense stellar radiation and gravitational locking. Mercury's polar regions, though small, hold some of the most surprising findings. The permanently shadowed craters near the poles maintain temperatures cold enough for volatiles to persist for billions of years. Radar reflections from these regions revealed deposits interpreted as water ice, likely delivered by comets or asteroids, or perhaps generated through chemical processes involving hydrogen implantation from the solar wind. Despite the scorching nature of much of Mercury's surface, these polar cold traps represent havens of chemical stability. Their existence highlights how even a planet baked by solar radiation can harbor regions of deep cold, creating a duality that seems almost paradoxical, a place where fire and ice coexist within a world too small to moderate its temperature. The journey of human exploration toward Mercury is also a story of innovation. Approaching such a sun-blasted environment demands spacecraft shielding capable of resisting temperatures that would destroy most equipment. Navigating into orbit requires precise gravitational assists because approaching the sun deepens a spacecraft's potential energy well, meaning it must shed enormous amounts of kinetic energy to avoid simply falling inward. Messenger tackled this challenge by using multiple planetary flybys, gradually reducing its orbital energy. Future missions will build upon these strategies, pushing the boundaries of what is technologically possible. As our exploration continues, Mercury remains a planet of layered contradictions. It is scorched yet icy, small yet internally dynamic, ancient yet marked with unexpectedly youthful features. It stands at the threshold between the sun's destructive power and the stubborn persistence of planetary geology. It acts as both a relic and a revelation, a survivor of early solar system turmoil and a guide to understanding the fates of countless rocky planets orbiting distant stars. Mercury's story continues to deepen as we explore the subtle interactions between its surface, interior, and the surrounding space environment. Though the planet appears at first glance to be a simple, barren rock scorched by relentless sunlight, ongoing research shows that it behaves more like a dynamic system shaped by numerous competing forces. These include the tidal influence of the sun, the heat-driven evolution of surface materials, the internal motions within its large metallic core, and the continuous bombardment of solar wind particles. Each of these factors adds layers of complexity that push planetary scientists to rethink how a small world can retain such an active geological and geophysical character despite billions of years of exposure to extreme conditions. One of the key areas where Mercury continues to surprise researchers is in its core dynamics. Although the planet's overall size is far smaller than Earth's, its core occupies a disproportionately large fraction of its interior. This metallic core likely contains a mixture of iron and lighter elements such as sulfur, silicon, or carbon. Instead of being fully solidified as once assumed, the core remains at least partially molten, and this internal fluid motion generates the planet's magnetic field. But the magnetic field is not uniform or symmetric. Instead, it is offset northward, meaning the magnetic equator does not align with the geographic equator. This asymmetry hints at unusual convection patterns within the core and raises questions about whether Mercury's internal structure includes stratified layers or compositional gradients that steer the flow of molten material. Understanding these internal processes is central to understanding not only Mercury's magnetism, but also how small planetary bodies can maintain magnetic activity over billions of years. Another element that shapes Mercury's character is its interaction with impacts. While every solid surface in the solar system bears the marks of ancient collisions, Mercury's proximity to the sun increases its exposure to both micrometeoroids and occasional larger impactors. High-speed micrometeoroid bombardment, especially from debris streams associated with sun-grazing comets, continually refreshes the planet's surface by churning the regolith and releasing particles into the exosphere. These impacts also contribute to the presence of rare species in the exosphere by vaporizing trace minerals. Meanwhile, larger impact basins scattered across Mercury provide clear evidence of a more violent early history. Some basins reveal multi-ring structures that indicate impacts of extraordinary scale. The Caloris Basin, among the largest known impact structures in the solar system, stretches across a huge portion of the planet and profoundly influenced Mercury's geology. The immense shock waves produced by its formation deform terrain on the opposite side of the planet, creating a region of chaotic, disrupted landforms. This weird terrain, as it is often called, remains a striking reminder of how profoundly a single impact event can shape an entire world. The long-term interplay between volcanism and impacts also shapes Mercury's surface evolution. Following the formation of massive impact basins, molten rock often surged upward to fill the depressions, creating smooth plains. These plains are different in texture and composition from the planet's older, more heavily cratered highlands. The chemical composition of these volcanic plains offers clues about the interior sources of Mercury's magma. The presence of sulfur-rich deposits suggests that, despite the intense heat close to the sun, Mercury retains significant quantities of volatile elements deep within its mantle or lower crust. This retention challenges traditional assumptions about how volatiles behave in early planetary formation environments, and it forces scientists to revise models of Mercury's early evolution. Even small differences in volatile content have large consequences for eruption style, magma viscosity, and crustal thickness. meaning that Mercury's modern surface is the cumulative product of a long and intricate geological history. As researchers delve deeper into Mercury's polar regions, the mystery of water ice in such an extreme environment continues to spark fascination. The combination of permanent shadow, high reflectivity, and stable temperatures creates conditions that are among the coldest in the entire solar system, colder even than parts of distant Pluto. In these dark craters, water molecules can remain stable for immense spans of time, accumulating into deposits that may be tens of meters thick. The origin of this ice may lie in the impacts of comets or the gradual buildup of hydrogen implanted by solar wind particles reacting with oxygen in surface minerals. The presence of organic molecules in these cold traps adds another intriguing dimension. Although Mercury itself is far too hostile to harbor life as we know it, the preservation of organic compounds and volatiles offers a unique record of the early solar system's chemistry. These polar deposits act much like cosmic archives, sealing away ancient materials that escape the otherwise destructive heat of the planet's sunlit surface. Thermal stresses on the day side of Mercury create an ongoing cycle of cracking, fragmentation, and rock breakdown. This mechanical weathering forms fresh surfaces that later interact with solar radiation. Over time, repeated heating and cooling cause rocks to exfoliate and split apart, producing fine dust and exposing layers with different mineral compositions. Because Mercury lacks an atmosphere to distribute heat or shield its surface from radiation, temperature gradients can occur over very small distances, leading to steep thermal contrasts. Even a single boulder can experience temperature swings great enough to influence its internal structure. This continual fracturing feeds into the broader cycle of regolith production, which in turn affects albedo, surface chemistry, and the generation of particles that escape into the exosphere. Mercury's orbital eccentricity adds further complexity to its environmental cycles. Because the planet follows an elongated orbit around the Sun, the amount of solar radiation it receives varies dramatically over the course of a single Mercury year. This leads to periodic differences in surface heating, interactions between solar wind and magnetosphere, and even changes in the length of Mercury's solar day relative to its orbit. The interplay between orbital eccentricity and rotational resonance means that at certain points in its orbit, specific longitudes face heightened solar exposure. These longitudes become hot poles, regions that endure prolonged periods of intense heating during each cycle. Meanwhile, other longitudes experience extended twilight or slower warming. These patterns shape the distribution of thermal stress features, influence the composition of the exosphere, and create subtle regional variations in surface aging. The magnetosphere of Mercury, though small, experiences sudden and dramatic fluctuations. The compression of the magnetosphere during solar storms can lead to direct deposition of energetic particles onto the surface. This bombardment alters the chemical composition of the uppermost regolith, sputtering atoms into the exosphere and creating transient enhancements in sodium glow. These events can also trigger magnetic reconnection in the planet's magnetotail, releasing bursts of plasma downstream. Because Mercury's magnetosphere is so compact, these reconnection events occur more frequently and more rapidly than similar phenomena around Earth. This offers scientists a valuable opportunity to study magnetospheric dynamics in a different and more extreme context, enhancing our understanding of how magnetic fields behave in intense stellar environments. As exploration continues through the Bepi-Colombo mission and future technological advances, Mercury remains a focal point for comparative planetology. The lessons learned from this scorched planet extend far beyond its orbit. They illuminate the early processes of planetary formation, provide insight into the geological evolution of rocky bodies, and contribute to the broader study of exoplanets orbiting close to their stars. Supermercuries discovered around distant suns show that planets with high densities in extreme orbital environments are common, not rare. By understanding Mercury in detail, scientists develop the tools needed to interpret data from these remote worlds, connecting the familiar with the unknown. Even as we gather more data, Mercury's identity as a planet of contrast becomes ever sharper. It is a world where extreme heat and deep cold coexist, where an iron heart generates a fragile but persistent magnetic field, where volcanic plains lie beside cratered highlands, and where the present-day surface tells a story shaped by both ancient catastrophes and ongoing processes. Mercury challenges simple categorization, revealing that even the smallest rocky planet can hold immense scientific significance.